Welcome to The Explainer. Today, we're doing something a little different. We're performing an AI autopsy. We're going to break down a brand new method that lets us trace an AI's decision-making right back to the source, all thanks to something called Bayesian Influence Functions. So picture this. An AI goes off the rails. It spits out something totally wrong or maybe even something biased. The number one question everyone asks is, why? Why did it do that? Well, to find the answer, you've got to dig in and trace that one bad decision all the way back to the single piece of data that caused it. This whole process, this quest to link an AI's actions to its education, actually has a name. It's called Training Data Attribution, or TDA. And honestly, it's one of the biggest puzzles we have to solve if we want to build AI that's safe and that we can actually understand. Now, for the longest time, researchers had a favorite tool for this job. It was their go-to method. But then the AI models got big, really, really big. And that old tool, it didn't just slow down, it shattered. So what was this old method? It was called influence functions. And the idea behind it was actually pretty neat. It was kind of like playing a what-if game with the AI. You take a fully trained model and ask, okay, what if this one specific piece of data had been just a tiny bit more important during training? Then you just measure how that little nudge affected the final outcome. Okay, but when you look under the hood at the math, you see the problem. The whole thing balances on that little H inverse term. That's the inverse of something called the Hessian. Now, you don't need to be a math whiz, just know this. The Hessian is a massive, complex object, and the entire method depends on being able to flip it upside down, mathematically speaking. And for the kinds of AI we use today, the ones with billions of parameters, trying to do that calculation isn't just difficult, it is flat out fundamentally impossible. And it's impossible for two huge reasons. First, the theory just doesn't work. For these huge AIs, the Hessian is often what mathematicians call singular. That just means it has no inverse. Trying to find one is literally like trying to divide by zero. And second, even if you could calculate it, the thing is just too gigantic to even store on a computer, let alone do math with. So, the old tool is in pieces. What do? Well, the researchers behind this paper had a brilliant idea. They decided to change their perspective entirely. Instead of looking for a single point, they started looking at a whole cloud. And here's the shift. The old way assumed there was one single perfect version of the model. But the new Bayesian way says, hang on, that's not right. It understands that there's a whole cloud, a whole neighborhood of really good, slightly different models that could have been created during training. And this, right here, is the aha moment. It's the genius of the whole thing. By switching from a single point to this cloud of possibilities, you get to swap that impossible Hessian math for something much, much simpler: covariance. Covariance is just a standard statistical tool that asks, when this thing changes, how does that other thing change with it? That's it. And that brings us to the hero of the story, the Bayesian Influence Function, or BIF. It's a completely new Hessian-Free method. All it does is measure the covariance. It just watches how the error on a training example moves together with the error on an output as you look across that whole cloud of models. It's elegant, it's robust, and it actually scales to modern AI.
Okay, that all sounds great on paper, right? But the real test, the only one that matters, is does it work in the wild? So let's see what happened when they put BIF in the ring against the current champion.
And the answer is, oh yeah, it works. The results are kind of stunning, actually. Using BIF on a giant language model, they could find these hidden threads of logic. For example, it figured out that the model's idea of the word she was most influenced by seeing the French word elle in its training data. Same for the number 3 and the word three. It's incredible.
So to prove just how good it is, they pitted BIF, the challenger, against the reigning champ, a method called EK-FAC. Now, EK-FAC is basically the best, most clever workaround that people came up with to deal with the old broken system. It's the state of the art. So let's look at the tail of the tape. Right away, you can see some major differences. BIF is basically plug and play. There's no big, expensive setup, and it works with any kind of AI. EK-FAC, on the other hand, is expensive to get running, and it's super picky about what kind of model it will even work on. But here's the real knockout punch: the speed. For a massive model with 2.8 billion parameters, EK-FAC takes about 300 minutes. That's 5 hours. BIF, 3 minutes. No, that's not a typo. It is literally 100 times faster. That's not just an improvement, that is a total game changer.
So you're probably thinking, okay, it's fast, but is it accurate? Well, in the ultimate gold standard test, where you actually retrain the model just to check your work, BIF is right on the money. It performs just as well and sometimes even a little better than the heavyweight champ, EK-FAC. So you get all that speed for zero cost to accuracy. All right, let's step back for a second. We have a new tool. It's faster, it's more flexible, it's just as accurate. So what? What does this actually mean for all of us and the future of AI?
Well, it means that, for the first time, we have an inspection tool that can actually keep up with AI development. It's scalable enough to handle the monster models we use every single day. It's flexible enough that it won't be obsolete tomorrow. And it's built on a rock-solid mathematical foundation, not a shaky workaround.
Here's the most important takeaway. For years, we've talked about AI as a black box. We couldn't see inside. This tool is the key to finally prying that box open. It means we can move from just hoping the AI works to a world where we can actually debug it, audit it for bias, and start to build systems that we can genuinely trust.
And all this progress leaves us with one final, very big question. If we can now trace every mistake, every single weird or biased thing an AI says, back to the exact piece of data that taught it that behavior, who's ultimately responsible for what the AI does? Think about that.